Hi, folks. Um, because our Monday and Tuesday discussions kind of went in a different direction than maybe I originally intended, great direction, a lot of fun talking about those different issues, real issues about power and electricity and whatnot. I didn't get to the second thing that I wanted to talk about during those lessons, which is what I want you to do some problems on. And that is problem 13 here. Okay. So a couch is pushed up a frictionless ramp onto a truck as shown. The mass of the couch is 20 kilograms. A 2,000 Newton force is applied parallel to the plane. That's the one shown. The ramp has an angle inclination of 37 degrees, and the ramp is 4 meters long, meaning this is the length of the hypotenuse here is 4 meters. And so this is a problem that we're going to be doing here where we're not moving along a flat plane anymore, right? So hopefully what you understand then is that the force of gravity is going to do work. Anytime there's vertical displacement, the force of gravity is going to do work. So this problem is meant to look into that. Of course, we've done problem 10 where the force of gravity did work, but that was a very straightforward. The mass is moving up, the mass is moving down. So here we're moving along this tilt and seeing, well, what implication does that have? So what I would like you to do is try problem 13 for a second, right? So shut the video off, try it, and then when you've tried it, turn the video back on, and then you can see me go through the problem, but I really do want you to try it for yourself. So pause yourself, and here we go. So theoretically, you pause the video, you tried the problem, and you're not just watching it through, theoretically. So let's hope you did that. So here we go. So I'm going to draw a nice big picture. I have my box here, and let's do our free body diagram since we know it's a work problem. This pen is running out of ink. And so I'm going to have my force of gravity acting straight down. I'm going to have my normal force here acting like that. We've got our applied force acting parallel to the slope, and there's my angle of the inclination of the slope. And I know that my displacement here, the displacement vector, is like that up the slope, okay? And so we've got that. Now notice here, if I needed to know the normal force, I would have to do a force problem in order to find the value of the normal force. And we know that that would end up, if I did then components, I would need to then do a force problem. I would need to find the components of FG there. We've done that in the past. But since this is a work problem, I don't need to do that. There's no friction in the problem, so there's no need to find the normal force. I'll find the normal force at the end just to remind you how to do that, though. So here we go. What are my knowns? I know the mass of that couch is 200 kilograms. I know the magnitude of the applied force is 2,000 newtons. I know the angle of inclination is 37 degrees. And I know that the displacement is 4 meters, because that's going to be what the displacement up the slope is. So, and that's to find the work done by a couple of forces. So first, the work done by the applied force. Nice and simple. Work done by the applied force, displacement, cosine of theta A. Now, I think here, you remember when I was teaching this the first time, I said that it might be helpful to draw little independent vector diagrams. I think this is, I know this is exactly what I was talking about. That's my displacement vector. You'll notice here that that force is along the inclination as well. And so that lets us know that the angle I want here is a 0-degree angle, right? I think it's very easy in this problem to want to be throwing 37 around, but we don't want to throw 37 around. We want to know what it is that we're talking about, that the theta in the work equation is the angle between the force and the displacement. So that gives us 8,000 joules there. Do that one in my head easy enough. I think all of us can. All right, so next I want to know the work done by gravity. So work done by gravity, force of gravity, displacement, cosine theta, g. And so now I recognize a little side work here. I need to find my force of gravity. So that's 200 kilograms, 9.8 newtons per kilogram, 1960 newtons. All right, so cool. So now if I do the displacement and I do FG, I find, oh, geez, what is that angle? Well, I know that that angle is the angle theta angle of inclination, and that's 90. So apparently this angle here is going to be 90 plus 37, okay? So what do we have here? Well, I have 1960 newtons. I have displacement of 4 meters. I've got cosine of this obtuse angle of 127. Now, before we throw that in our calculators, let's think to ourselves, cosine of an obtuse angle, what do I know is true about the cosine of an obtuse angle? Hopefully, what you remember is that the cosine of an obtuse angle is going to be negative. So that means I'm going to have negative work here. So is that going to make any sense? Well, let me just quickly do this calculation here. You can see me doing this on the side there, and I get negative 4718 joules. We'll just round it there. Okay. So does that make sense? Well, hopefully you're saying yes. The action of this applied force going along with the displacement is trying to speed up the object. But if you think about it, as an object is going up an incline, it makes sense that gravity is trying to slow it down. Anytime the action of an individual force would attempt to slow down the object, we would expect that that force does negative work. It's trying to remove capacity due to motion from that object to affect the environment. So that result makes a lot of sense then in terms of what's going on. Last thing we have here, work done by the normal force, Fn delta S, cosine of theta n. And so if I were to draw my little side diagrams there, okay, clearly what I'm going to have is that this is going to, we know that theta n is going to go to 90. So I'll just do that plug in there. And this becomes 0 then because that whole term goes to 0. So there we go. Nice and simple there. I don't have to find the normal force, but let's say I had to find it for some other reason. Let me just remind you of how you would do that. I would need to make a declaration, right? Positive y. I would draw in my components, FGY, FGX. I would know that this is the same theta as that. And then I would do net force in the y direction is equal to MAY plus normal force minus FGY is equal to MAY. The AY would go to 0 because it's not accelerating along that axis. Oh, I'm sorry, I'm off the screen there. And then Fn would equal FGY, which is, of course, FG. In this case, if we look at the triangle there, FGY is on the adjacent side. So FG cosine of that angle. So I put in my 1960 times the cosine of 37, and I would find out what that number is if I needed it. I don't need it. All right. And so here we go. Let's continue with this problem. I now know all the works, so I can find the net work as the work done by gravity plus the work done by the applied force plus the work done by the normal force. So the work done by gravity is negative 4718 joules. The work done by the applied force is 8,000 joules. No work is done by the normal force, or I could just zero it out up there if I didn't want to write that term down here. I've got 3,000, what is it, 3,282 joules is the net work done. Now, it should be said here that the work done by the applied force in magnitude is greater than the work done by gravity. That's a good thing because if that object was at rest, you know, and the work done by the applied force wasn't bigger than the work done by gravity, I'd have a problem because I would end up with a change in energy that was negative if it didn't already have energy, right? If it had a kinetic energy up the hill already, that could happen, but there it is. So I've got that work net. And so then the last part of the problem is to find if the object started at rest. Yep. Find the speed at the top of the incline. So we know that work net is equal to delta KE. And so then I have 3282 joules is equal to 1/2 mv final squared minus 1/2 mv initial squared. Get into the habit of writing out the total delta. That's equal to 0. It's not always equal to 0. In the homework I gave you a couple days ago, people assumed that the VI was equal to 0, and so we're just conflating this term as always being equal to 0, but that's not true. Let's not make that assumption. Always write out the entirety of the concept and then apply the specific condition, okay? And so I can put that there and then throw that in my calculator. So that's going to be 328.2 is going to be divide this, well, let me just do it. 3282 divided by 100. I could have done that in my head, square root of quantity. So VF at the top, plus or minus, reject the minus because I'm looking for a speed, 5.73 3 meters per second. And there's the speed at the top of the hill, right? So inclined planes, not really that much more difficult, right? Because all you're doing is recognizing the angle between them. Just as a thought here, if I had my object at the top of the incline and had to go down the incline, well, that's going to be a little bit different, because if I look at what I've got going on there, if I were to draw the displacement vector and the force of gravity concurrently, you would see that the angle, if this angle, let's say it was that same 37-degree angle, this angle is not the 127 it would be. In fact, I would need the work to be positive, because gravity is clearly going to speed this object up as it's going down the incline. I would need work to be positive, meaning that the angle, I would need an acute angle in the work equation, because cosine of an acute angle is a positive number. So what is this? Well, that's just the complement of that angle. And I think that if you just think of the triangle here, that's making that's clear. Or if you want to think of it in another way, if this is the horizontal and that's a 90-degree angle, and this is the angle of inclination of the hill, I think it makes sense to make this 53. But the important thing is, don't just throw the angle around that's given. You have to think about the meaning of that angle in the work concept. So with that, I have a couple of homework problems, some on power and one with an inclined plane for you to do. So there we go. And let me remember how to stop this video.